So let's pick up from where we just left off. We said, hey, if we want to compute the volume of a k-dimensional manifold, here's how we do it. We figure out a way to describe this manifold. We take the Jacobian of that description, that parameterization. We multiply that Jacobian by its transpose. We take the determinant of that, then the square root of that, and we integrate that over the parameter bounds that adequately described this manifold to begin with, and voila, we have volume. And you might be wondering, well, there are sometimes different ways to parameterize the same manifold, and you told me last semester that I could choose my own adventure, and I did not lie to you. No parameterization, as long as it follows all the rules of parameterizations, is necessarily the right one. Some are easier than others, but for example, you could describe the quarter circle using a Cartesian coordinates to inspire you. Maybe you want y to be t and x to be square root of 1 minus t squared, right? Or you could use polar coordinates to inspire you and say, okay, x is cosine t and y is sine t, and t is going from 0 to pi over 2. Note that the parameter bounds were different for the former description where t was going from 0 to 1. But in a simple case like that, when you'll find that the integrals that you have to evaluate, because you're using different parameterizations, they're going to have different Jacobians. The product under here is going to be different. The determinant of that matrix is going to be different. The square root of the determinant of the matrix is going to be different. The bounds that they are being integrated over are going to be different. But believe it or not, when you evaluate it, it will give you the same answer. Boom. And you probably suspected that we wouldn't lead you down this primrose path and tell you that all parameterizations are equally good, without actually meaning it. So the real issue is that you can really convert between parameterizations just by doing a change of variable. And so when we look at this, say we have right here, this is our manifold here, this is a point on our manifold, and we have two different choices of parameterization. And so one of them comes from this parameter space U, and gamma 1 maps from that parameter space to the point on the manifold. And this is another choice of parameterization, comes from parameter space V, and gamma 2, the other choice of parameterization, maps from V to the point on the manifold. And so you could set up two totally different looking integrals because they involve two different gammas, gamma 1, gamma 2, two different Jacobians, two different determinants, two different square roots of the determinant, two different types of parameter bounds here. And these will actually end up being equal. And of course, the secret to this proof is to introduce a change of variables function phi. And phi is going to move us from one parameter space to the other. And we realize that gamma 1 could be rewritten as a composition of functions. It could be gamma 2 composed with phi. So you would apply a change of variable first and then apply gamma 2. That's two different ways to have the same effect as gamma 1. And so then you basically use everything you know. You just use the change of variables formula, use the product rule for determinants and the chain rule, and you complete the proof. And this proof we're going to go through in class, and as you probably suspected, this is actually going to be your 18.2, showing that you can choose whatever parameterization you like, just as long as they are good, strong parameterizations that follow all the rules of parameterizing, and you set up the integrals accordingly. You'll end up with two different ways to evaluate the same volume correctly. Now you will get quite good at parameterizing different surfaces, but here are just some useful parameterizations to have as a point of reference, and you'll definitely learn them and feel quite comfortable with them, especially after this week is over. Here right off the bat we have a circle of radius big R. And I'm going to fix this typo right here, so if you are looking at your notes, probably already says R, big R cosine theta, and big R sine theta, but I'm going to write them in right now. Note that big R there is not a variable, it is a constant. And so this is what our d gamma looks like, and this is what our square root of the determinant of d gamma transpose d gamma looks like, and so we'll be integrating that over the parameter bounds, right, which are from 0 to 2 pi, and of course there you go, right, 2 pi r is what you would expect for the circumference of a circle of radius big R. If you're going for something that's a little more complicated, maybe x squared plus y squared minus z squared equals 0, with z being between 0 and 1. This is the upper part of a cone from 0 to 1. And so you want to build this off of polar coordinates. Note here, this is how we want to parameterize this: r cosine theta, r sine theta, and r. D gamma looks like this. And then we have the determinant of d gamma transpose d gamma is the square root of 2 times r. For a sphere of radius big R, we're going to use spherical coordinates. We've already gone through what this looks like, but you're going to get r squared cosine phi. And I want to point out before we even move on further down the page that when we're dealing with a curve, right, what we have here is a single parameter that maps to, maybe there's an x and a y and a z value, but it is a single parameter that manages a curve. When we're dealing with a surface, whether it's a sphere or a cone, we have two parameters, and they manage a surface which has two-dimensional volume. See where that's going? And then when you have three parameters, you have an object or a manifold that has three-dimensional volume. And so you always want to remind yourself of that if you're someone who finds yourself struggling with parameterizations, that 9 times out of 10, a big clarification comes from reminding yourself, what are you trying to describe? A curve, a surface, or a solid? You know, if it's a surface, that means that's something that has two-dimensional volume. And so it needs two parameters to describe that manifold. So keeping that in mind, let's take a look at some more. Here we have an example of if we get a surface by taking a graph f of x and revolving it around the x-axis. Now, people get a little confused, you know, what does this look like? So we have our axis here, and perhaps our function looks something like this. And when we go about revolving it around here, you're going to get, you know, things that look a little bit like this. Note that x is going to be one of the parameters, and in the yz plane, because that's really, we're moving from R2 into R3 in examples like this, but in the yz plane we have circles. And these circles, the circle's radii changes based on the function value at that particular point. So that's how you see f of x cosine theta and f of x sine theta in the y and z components. If you take a curve parameterized accordingly and you rotate it about the x-axis, similarly x is untouched, but then depending on y, right, which would be like how we envision the function value, we want to rotate around the x-axis, it's going to create circles there as well. So we have v of t cosine theta, v of t sine theta. And then a special case of the above, a torus, and I'm going to call it out right now. Paul loves a good torus. I don't know why, but he said it my year. He just loves the parameterization for a torus. Learn it, live it as your truth. Don't be surprised if it comes up on quiz number 2. It certainly did my year. So we take a circle of radius r in the xz plane that's centered at x equals big R, z equals 0. What does that look like? Well, there is my blue circle of radius r centered at big R, comma 0, and then it gets rotated about the z-axis to get a torus. That is a completely terrible artistic rendering, but you understand what's happening there. Note that the parameter u goes from 0 to 2 pi around the original teeny tiny circle. So it's in there, whereas v goes around the big circle. And so you have both u and v going from 0 to 2 pi, u being the pink part, v being the blue part. And so you end up with this being the determinant, the square root of the determinant of d gamma transpose d gamma. It's great to know this as a check, but certainly if this showed up on a quiz, you would need to know how to parameterize the torus and how to compute this as well, from which you can calculate the surface area of a torus. So I would say you'll get a ton of practice parameterizing surfaces, solids, curves, things of that nature in lecture, in section, and on your homework. You'll feel quite comfortable with it, but of course if you have any questions at all, please don't hesitate to ask. Thanks, guys.